So we are constructing antiderivatives. That is, we're trying to figure out what function did we take the derivative of to produce the given function. Now, of course, all of this is also in the context of all that you've learned so far about area under the curve and left sums, right sums, etc., etc. But right now, the focus is on just constructing these antiderivatives. These four examples will provide some insight into how you can go about doing that. In number one here, the first issue is that you are not allowed to just integrate that factor, x plus 2 squared, and then integrate that factor, the square root of x, and call it good. If you tried that, you would see that the function that is produced, in order to take its derivative, you would need to do a product rule, and that product rule would produce something that is not the given function that you see here. So instead, what we do is my 10 seconds of algebra thing. So first, x plus 2, the quantity squared. Just go off on the side somewhere and do x plus 2 times x plus 2 and FOIL everything out, and what you'll find is that it's x squared plus 4x plus 4. Then we will take the square root of x and distribute it through. Now remember, the square root of x can be thought of as x to the 1/2. And remember that when you multiply, say, x to the 1/2 times x squared, you'll add those exponents. So in the first case, we'll get x to the 2 plus a half, 2.5, or 5/2. We'll get 4x to the first plus a half is 1.5, or 3/2. And then just 4 times the square root of x, or 4x to the 1/2. Now I have 1, 2, 3 distinct terms separated by the pluses here, and you can, by one of the theorems presented last week, you can integrate each of those separately. That's fine. So, what did I take the derivative of to produce x to the 5/2? Well, in taking the derivative, you decrease the power by 1 to 5/2. So now we'll increase the power by 1 to get to 7/2. Now when you take the derivative, you would to get to 7/2. Now when you take the derivative, you would bring the 7/2 out front, and notice up here the 7/2 didn't survive the differentiation process. So there must have been a 2/7 out front. 7/2 comes out front, runs into the 2/7, canceling everything out, decrease the power to 5/2, we're good. Now the next term, the 4 as a constant multiplier or coefficient comes along for the ride, and we'll just focus on the x to the 3/2. In taking the antiderivative, we'll add 1 to 5/2. Now in taking the derivative, that 5/2 would have come out front before being decreased to 3/2. So since it didn't survive that process, there must have been a 2/5 out front. Now I'll clean this up and simplify it at the end, but for now, that's good. Same thing here. 4 comes along for the ride. X to the 1/2 gets increased by 1, which would make it 3/2. That 3/2 had to go away in the differentiation process since there's no 3/2 out in front here, and the 2/3 will take care of it. Don't forget your plus c. So to make it look all pretty, we'd have 2/7 x to the 7/2. We'll have 8/5 x to the 5/2, and we'll have 8/3 x to the 3/2 plus c. There you go. Number 2. Just wanted to throw some trig and some exponential functions at you to see if you could do it. So let's work through it. Now, there's no algebra you can really do here. Well, a little bit on this final term, but on the first 2 terms, no algebra. Let's just think. What did you take the derivative of to get e to the 2x? Well, the derivative of e to the 2x is e to the 2x. That was one of the beautiful things about the exponential function e to the stuff. But the chain rule says we need to go inside this power here and take the derivative of the 2x, which would be 2. So the derivative would be e to the 2x times 2. And the times 2, again, something happened in that process. Must have been a 1/2 that took care of it. Similarly here, The derivative of what gives me sine of 3x? Well, the derivative of cosine of 3x. The derivative of cosine is negative sine. Oh, so I need to remove the negative sign with a negative sign. So the derivative of cosine of 3x, negative cosine of 3x, is sine of 3x. The derivative of 3x would be 3, and the 3 didn't survive the process, so there must have been a 1/3 out front. On this last one, notice it's the square root of 5 times x, or in other words, 5x to the 1/2. What did you take the derivative of to get 5x to the 1/2? Well, the 5x must have been raised to the 3/2 as we increase the power by 1. When we bring the 3/2 out front, it needs to go away since there's no 3/2 out front up here. So it must have been a 2/3. So look at this right here. 3/2 comes out front. Everything cancels out with that 2/3. Decrease the power by 1 to 1/2. All good. But then the chain rule would say go inside and take the derivative of 5x. And again, there was no 5 out front. The derivative of 5x is 5. There's no 5 out front. So what took care of the 5? Well, a 1/5. Let me squeeze in a 1/5 here as well. Plus c. So to make it all look nice and pretty, we'd have 1/2 e to the 2x minus 1/3 cosine of 3x. And then this 1/5 times 2/3 would be 2/15. 5x to the 3/2. Don't forget your plus c. Number 3, pretty classic case here. 10 seconds of algebra. You can distribute this division by t. So think of it this way. If you had t cubed, t times t times t, and divided by t, what would be left would be just a t squared. Minus 3t divided by t plus 1/t. Now we have 3 little terms. Each one we can anti-differentiate reasonably easily. What did you take the derivative of to get t squared? Well, increase the power now in the antiderivative. The 3 coming out front didn't survive, so it must have been a 1/3 out front. Minus, what did you take the derivative of and just get the constant 3? Well, the derivative of a linear function, 3t, is the constant, just 3. And then 1/t. What did you take the derivative of to get 1/t? Well, the natural log of t does that. And this is sort of a remember from last semester in Calc 1. Hopefully you remember. The derivative of the natural log of some stuff is 1/the stuff. Don't forget plus c. Alright, finally number 4. What did you take the derivative of to get 3x? Well, the 3 will just come along as a constant multiplier coefficient on the x. We'll increase this power of 1 to 2. The 2 coming up front didn't survive the process. There must be a 1/2 out front. Now this one is just sort of again from last semester, maybe you remember. What did you take the derivative of to get secant squared? Well, it was tangent. The derivative of tangent of whatever, in this case 3x, is secant squared of 3x. But then we'd have to go inside and take the derivative of 3x, which is 3, and the 3 didn't survive that process, which tells us there must have been a 1/3 out front. And then what did you take the derivative of and just get 1? Well, x does that, and then plus c. So to make it look all nice and pretty, we would have 3/2 x squared, 1/3 tangent of 3x, minus x plus c. So